Hey, welcome to The Explainer. Today, we're going to look at a totally invisible process that happens to pretty much every carton of milk you buy. It's the secret reason your milk is so perfectly smooth and consistent, from the first pour right down to the last drop. We are talking about milk homogenization.
So, have you ever wondered about this? It seems like such a simple question, but the answer is surprisingly complex. If you've ever had real, farm-fresh milk, you know that it naturally separates. You get that thick layer of cream right on top. But the milk in your fridge, it just doesn't do that. So, what's the deal? That's exactly what we're going to get into.
All right, here's the game plan. First, we'll tackle the cream-free challenge, basically why the industry decided that cream layer was a problem that needed fixing. Then we're going microscopic to see how they actually shrink the fat globules after that. After that, we'll take a look inside the homogenizer itself, get into the wild physics of the pressure involved, and wrap up with how you keep these powerhouse machines running.
So here's the thing about milk in its natural state. It's not uniform. If you just leave it alone, the lighter part, the fat, the cream, it floats right to the top. Now that might sound kind of nice, but for a global dairy industry that's all about consistency and a long shelf life, that's a huge headache. Their solution? Homogenization.
And at its core, that's really all it is. Homogenization is a purely mechanical, physical process. We're not talking about adding chemicals or anything like that. It is all about brute force. The whole goal is just to smash those fat particles into pieces so incredibly tiny that they can't rise to the surface anymore. They just stay suspended evenly throughout the milk. And this is way bigger than just the milk you drink. This process is absolutely fundamental across the entire dairy aisle. Homogenization is what gives coffee cream that whitening power. It helps create the super stable, smooth gel in yogurt, and it stops fat from separating out in ice cream mix. It is the hidden hero that guarantees the texture we expect from dozens and dozens of products.
Now, to really understand how this works, we have to think small. I mean, like microscopically small. Because at its heart, homogenization is about violently and fundamentally changing the physical structure of fat in milk.
The sheer scale of this transformation is just incredible. Before the process, you've got these fat globules that are about 2 to 6 microns in diameter. They're big enough and light enough to float up, but afterwards, they're smashed into tiny particles, less than 1 micron across. They become so small that the natural random jiggling of water molecules, it's called Brownian movement, is enough to just keep them suspended pretty much forever. They simply can't rise to the top anymore.
So how on earth does this happen? Well, it is an unbelievably violent event. First, the milk is shot at insane speeds. We're talking up to 200 meters per second through this incredibly narrow little gap. That combination of speed and pressure literally stretches the fat globule out of shape until it gets all wavy and unstable, and then it just completely disintegrates into a cloud of tiny new droplets.
And get this, there's another amazing force at play here: cavitation. As the milk blasts through that tiny slit, the pressure drops so fast that tiny vapor bubbles actually form inside the milk. But the instant the pressure goes back to normal, those bubbles violently collapse, they implode. And these implosions create these intense little shock waves that are a huge part of shattering the fat. It's like a microscopic demolition job happening inside your milk.
Okay, so we know what happens to the milk, but what kind of monster machine can actually create these kinds of extreme conditions? Let's take a look inside the homogenizer itself.
It sounds simple when you put it that way, but what we're really looking at is a piece of seriously heavy-duty precision engineering. I want you to picture a powerful engine with a bunch of pistons all working together to build up this immense pressure, forcing a constant stream of milk through a tiny, specially designed gap we call the homogenizing valve. Now, a lot of modern homogenizers actually use a two-stage process. The first stage is the main event. That's the huge pressure, 150 to 200 bar, that does the initial shattering. But here's the problem. These brand new, tiny little fat globules, they have a tendency to want to stick back together and form clumps. So they add a second stage at a much lower pressure, maybe 20 to 40 bar, and its only job is to break up these new clumps, making sure the final product is perfectly smooth and stable.
Let's dig into the numbers a bit more, because the physics behind all this are truly impressive. We're talking about forces that have very real, very measurable effects on the milk.
The pressures we're dealing with are just enormous, sometimes reaching up to 250 bar. To put that into perspective for you, that is over 3,600 psi. That's more than 100 times the pressure in your car's tires. Just think about that. Containing and controlling that much force is a massive engineering challenge, and it's all being applied to milk to permanently change its structure.
And, basic physics, right? When you compress something and create that much friction and turbulence, you are going to generate heat. This isn't some weird side effect. It's a direct and totally predictable consequence of all the energy being pumped into the system.
In fact, this relationship is so predictable that there's a reliable rule of thumb in the industry. For every 40 bar of pressure you apply, the milk's temperature goes up by 1 degree Celsius. So, at 200 bar, the milk comes out 5 degrees warmer. This isn't just a fun fact. Dairy engineers have to plan for this temperature increase in their whole plant design, integrating it with pasteurization and cooling to make everything as efficient as possible.
So, a machine that operates under these extreme pressures, day in and day out, yeah, it requires some serious attention. This is not a set it and forget it kind of thing. Proper maintenance is absolutely critical for safety, for efficiency, and for the quality of the final product.
And this right here is the heart of the machine, the valve face. On the left, you can see a healthy one. It's smooth, it's even. This allows for consistent pressure and great results. But on the right, that's what happens over time. The incredible force of the milk literally erodes the metal, carving grooves into it. And once that happens, the machine just can't hold pressure anymore, and the quality of homogenization just falls off a cliff.
That's why the upkeep checklist is so rigorous, and every single item is critical. Checking oil levels in cooling water isn't just routine. It's what stops the pump from seizing up under that immense strain. Calibrating the pressure gauges is essential, because if your pressure reading is off, your entire product is off. And maybe the most important check of all is testing the safety release valve. That thing is the last line of defense preventing a catastrophic failure under thousands of pounds of pressure.
All right, so let's tie this all together. First, we learned that homogenization is a physical process that stops cream from rising by absolutely smashing fat globules into microscopic bits. Second, it does this using a crazy combination of extreme pressure, high speed, and the violent implosion of these things called cavitation bubbles inside a super specialized valve. And finally, these absolute workhorse machines demand constant, precise maintenance to work safely and to get the job done right.
So the next time you pour a glass of milk, you'll know about the incredible journey of pressure and physics it went on just to become that perfectly smooth liquid you expect. It really makes you wonder, doesn't it? Homogenization completely reshaped our milk. What other invisible processes are hiding in plain sight, defining the food we eat every single day? It's something to think about.